It was bad weather pretty well all around the public meeting. So that happened mid-December. Okay, so the timeline is close the bridge October 16th, pretty well abandon any thought of rehabilitation by November 15th, and now we're coming up with an emergency ferry, coming up with a demolition strategy, and designing a new bridge. Yep. And so this is a slide right from the public meeting. These were the alternatives we came up with, less this one. At the what we called the pre-public meeting, the pre-PAC, we had the Public Advisory Council. We had a pre-meeting with some of the resource agencies, and I would have to say we're replacing an important historic bridge. Historic preservation, the historic preservation community was very well represented on the PAC, and I have to say we're wonderful people to a man. One of the folks from Vermont, Scott Newman, who's really a character in a lot of ways, when we were looking at these five, he looked at this and he said, you know, I like this one, but it seems somehow unfinished. Yeah? And I couldn't agree with him more. It didn't seem finished enough. It was missing pieces. Yeah? And so that was at 8 o'clock. It was a Tuesday night, and the meeting was Wednesday. No, that was a Friday night. The meeting was the next Saturday. So that night we came up with, we sort of sketched it up on paper on a flip chart, and got on the phone with my poor rendering guys, who stayed up all night and developed this modified network tied arch. And we had the public meeting the next day. We even developed these overlays, and this was in a presentation similar to this, where because we didn't have any of the boards and posters because we had made it the night before, but this was the resounding favorite. And what I would say is when I say resounding, and talk a little bit about public involvement, in a major city like New York, if you have a public meeting for a huge project, $1 billion project, and get 100 people to show up, you are thrilled. We had 600 people show up, and in terms of voting on alternatives, we had roughly 3,200 to 3,300 people vote on the bridge. Now, the bridge traffic per day is 3,500 people. Now, if you imagine like the Verrazano-Narrows Bridge, that would be like having 300,000 people vote on the bridge carries that many people. Pretty well everybody who uses the bridge seemed to have voted. That's legendary, I would say, in public involvement. And our public involvement consultant, I have to say, was beside herself. But what really struck us, I would say, you know, everyone's suffering, and people were so gracious about our work to date to get to this point that it was, I mean, Ruth Fitzgerald, our public involvement specialist, said, you know, and she just retired, I've been doing this for 35 years. I have never seen anything like it. She said, for people to clap for us, people don't clap at public meetings. Yeah, that's not, people yell at you at public meetings. They're disappointed with you. Clapping, and after all what had happened, was really mesmerizing for us. Now, I say this all the time, if it were one side of the lake, it would be the most environmentally sensitive project I've ever worked on, yeah? Both sides, one side is worse than the other in terms of archaeological resources. This is like, I don't know, building a bridge next to the Sphinx or something. We have cultural resources, pre-Revolutionary War forts, Revolutionary War forts on the New York side, right adjacent. You can throw a stone into the middle of the fort from the New York side. And on the Vermont side, we have 10,000 years or nearly so of Native American history. And when I say it's right there, we had University of Vermont go out and take a few samples of the Vermont shoreline. And this also never happens. Every shovelful had an artifact in it. Yeah, every single shovelful. That's, again, I've been doing this a long time. That's never happened. Yeah, so now to get resource agencies aligned, yeah, to permit such a project in a tight time frame is no a mean feat. And if you combine this with the idea that you've got 2 states, 2 regions, 2 federal highway, so 2 federal jurisdictions, the Army Corps and the Coast Guard all in the mix. We had 40 resource agents. A typical project in a complicated environment has a dozen, okay? It just gets multiplied by 2 because you have both states. Now, again, this was supposed to take 5 years. The permitting process, absolutely nothing skipped, took 6 weeks, yeah? And it's stunning. I can tell you, the chief engineer from the Coast Guard came to my office in New York. That never happens. That will never happen again, yeah. I know that, well, I'm still stunned about it. Yeah, that, usually if you get them to answer the phone, you celebrate. Yeah, mostly because these are hugely under-resourced agencies. And the state of emergency, I should also say, was lifted by both states. So we were no longer in a, you can break some of the rules and everyone is, let's say, focused. But I would say we had meetings with resource agencies where every resource agency was in the room at the meeting. That's incredible. An incredible amount of synergistic work, and I think our federal government could learn from such things. Yeah, when there's a will, there's a way. And so ultimately, we decided as a project that, and the Public Advisory Committee made a recommendation to NYSDOT. NYSDOT is essentially the lead agency, or the VTrans followed on this one. That NYSDOT selected this bridge and that we were under final design. Now, of all of those alternatives that I showed you, the range in costs was somewhere on the order of $60 million to $75 million, yeah? And so the most expensive, we also feel, and this is part of my work, that bridges shouldn't be expensive, yeah? And there's a reason they shouldn't be expensive, and that's because they're made with your guys' money, yeah? I design things with other people's money. And in my view, that needs to bring a certain amount of austerity to a project and also a certain amount of cleverness to a project so that you're not spending more money than you might, yeah? Now, this is quite a site, so to do a very rudimentary, very plain bridge, I think also is not right. But our goal was to keep the costs of whatever we did to be very, very close to an austere girder-type bridge. And ultimately, that's what worked out. And I want to take you a little bit to how we got there. The cross-section and what we were, and we had a little bit of disagreement at public meetings about this, but I would say here again, the public was really supportive of us getting things going. So whether the pedestrian walkways should be 8 feet or 10 feet, or whether you should have wide shoulders or bicycle lanes, all of that requires agreement, and sometimes that can be contentious. Here, it wasn't at all. In terms of navigational clearance, the Coast Guard tells you what the navigational, it's not a discussion, that's an edict, yeah? And so part of even that flexibility that the Coast Guard showed, in the end, we provided the same vertical clearance as the existing bridge. And if you remember the opening slide with the Lois McClure, I always take heat about that because my rendering, the folks who do the 3D visualizations, he's a boat addict, and so he spent more time, I say, on the boat than he did on the bridge. But essentially, the span is about the same, but this strategy of using what I call rigid frames, these delta legs, allowed me to make the span much shorter than the existing bridge, yeah? So the long span, the arch, is really only 300 feet, yeah? This is a good strategy, saves quite a bit of money. So the arch is as small as possible. Yeah, and so this, coming to agreement as to what the bridge is, the existing bridge, by the way, the lateral bracing had been hit by, I want to say, farm equipment mostly, but overheight vehicles, I mean, I think every lateral had been hit, so I think there's less likelihood of that happening. Now we got it really out of the way. A lot of times we're building bridges, especially bridges in the 20s and 30s, don't have enough clearance. I mentioned about this icing business, and so we have sloping piers so that the ice rides up and breaks off, and there's granite, yeah, facing the foundations. This, in my view, is the right thing to do. I also got very interested in my post-September 11th, I got very interested in the way bridges fail, especially from intentional attack. And so I've done a lot of work on protecting bridges from terrorism, and also a lot of work on looking at how bridges fail and how we might make them safer. And some of those characteristics are integrated into the design, and I kind of want to walk you through how I got there. These are 3 bridges that were all taken down in 1 month in Iraq, yeah? It's the untold story is that the insurgents, or whatever the proper name for the resistance in Iraq, was taking out their own infrastructure to make it harder for us to carry out our mission. And so that gives you a sensibility about how fragile some structure types are, but there's been only a few studies in the United States and really a few studies in the world about why bridges fail. This to me is shocking. We should know exactly what causes bridges to fail and what sort of bridges fail more likely than other bridges. And so this is a table which shows essentially trusses actually are quite vulnerable structures. Yeah? Trusses are fragile in their own way. About a quarter, we had 500 failures in a 12-year period, and a quarter of them were trusses, even though the percentage of trusses, it's like 1%. So they fail at about 20 times the average of any other bridge type. So trusses, in my view, in the way they were designed, have some intrinsic weaknesses. Also, the right screen is the stuff we don't design for, yeah? And everything in yellow. So 2/3 of what we don't design for causes bridge failure. We do a pretty good job when we know the white stuff. When we know what we're designing for, we have very few failures. When we don't know what we're designing for, we have lots of failures. But lots of strange things happen. This stuff is hard to make up. This is a coconut truck accident on a bridge in Mexico where the coconut's caught on fire, and this cable here actually is coated with its protection measure actually is flammable. So that caught on fire, and the cable failed, and luckily 2 or 3 cables didn't fail, or the bridge would have failed. This is hard to predict. This is Katrina. Yeah, you don't expect, you know, we look at vessel impact. We don't expect a vessel to be an offshore oil platform that had come on board. Yeah? Now, the good news is that it did very little damage to the bridge, and cables are wonderful for impact, actually. They do a great job against impact. So cables have their weakness, but also their strength. Yeah, weakness is, is fire. And then everyone is familiar with the failure of the I-35 bridge in Minneapolis, Minnesota. What people don't realize is that it was the failure of this plate, of this connection, of this bridge. Yeah? So this is where trusses for B are fragile. Yeah? One small element can fail, and it's a link in a chain where all the links have about the same safety. Yeah? And in my view, this is not the way to design, especially now, when this bridge was designed, we didn't understand some of these ideas. Nowadays, we should be looking hard to make sure that can never happen. And some of the features that are incorporated in this bridge are designed just for that reason. So to give you a little bit some of the DNA, the beginnings of the Lake Champlain Bridge and other projects, this is a bridge over the Ohio River in West Virginia, and this was the first time I used crossed cables, yeah? And this is a big bridge. This has got a main span of about 900 feet. But this was a bridge where we were required to make the bridge withstand the loss of any one cable, yeah? And we imposed this on ourselves. We thought, you know, it's safer. I was doing all this work in security and about cable failures, and I thought, well, we should design a bridge so that the cable can fail and the bridge won't collapse. And so we did all of these analyses, and this is one where not only can you fail one cable on this structure type, and you'll see the bridge deflect, and then you'll see the cable fail, and it'll spring, and you'll see the bridge shake around a little bit. But not only can you fail one cable in this bridge type, but what was amazing to me is you could fail the next cable and a third cable and still not change the behavior of the bridge. Yeah, the bridge would still be able to support live load. And this became, to me, something wonderful. Here's a structural system that's much, much safer than trusses. If you imagine taking a diagonal out of a truss, the truss fails. That's what happened on I-35. It wasn't the diagonal, it was the connection to one of the diagonals that failed. Here we're taking out 3 adjacent diagonals and the bridge still survives. So this is the idea behind network arches. Behind arches which don't have vertical cables, they have cables that cross. And if you happen to see the bridge on your way through Port Henry, you'll see these crossing cables. And I argue that in many forums, engineering forums, that we should not be allowed to design bridges with vertical cables because they don't have this intrinsic safety. There's no change in material costs, a little change in fabrication, but not much. And so part of doing the research on inclined cables was realizing that this was invented by a cute little Norwegian man who we've since become good friends, Per Tveit, and he had done 2 of these bridges in college and then had become a university professor and stopped, or just after college, had become a university professor and stopped designing. Well, these are very, very slender bridges. You can see the arch almost disappears, yeah? And that's because these cables provide the arch with wonderful stability, yeah? So it makes the bridge more stable, and you can make the rib very, very shallow. Well, to me, there's this interplay between how shallow the rib is and how many cables you can lose, and I'm interested in how many cables you can lose. So there are other precedents. If you think about it, the town lattice truss, the covered bridge strategy is exactly this strategy of crossing cables. And I have to tell you, I've been on a lot of timber bridges, and usually the diagonals are rotted to hell, yeah? And it's amazing that these bridges stay up. And one of the reasons these bridges stay up is for the same reason you can lose a couple cables next to each other. They're intrinsically redundant. They can redistribute loads. It's a fascinating, let's say, capability that a structural system can have. And for me, there's something nice about having covered bridge DNA in the Crown Point Bridge as a replacement. We've only done a few steel trusses. These are mostly railroad bridges that use the same town lattice idea, and I don't know why. I'm on the prowl for the right railroad bridge job where I can do a lattice truss, because I think they have wonderful opportunities. Now, a little bit about austerity. I spent the last 5 years redesigning over-budget pedestrian bridge projects, yeah? And there's something that I've learned in all of that I hope comes across with Lake Champlain. And mostly it's that if you want to get cost-effective, we as engineers have always been optimizing materials. We say that's in our control, yeah? So we're designing bridges with less materials or trying to optimize materials. And it seems to me silly in a way, because most of the expense of bridges nowadays is in labor. And we as bridge engineers are not very respectful of what it takes to put a bridge together often. And so these are 3 projects, and I'll take you through each one, where they were redesigned, in most cases for half their cost, yeah? So people don't believe this, that just through engineering, you can take a project. In the first case, the Bob Carey Bridge in Omaha, that's a $47 million bridge, redesign it for $22 million. And actually it was more like 19, because that redesign was actually, we had to redesign it, so we had to spend the engineering dollars to redesign and inspect it. So the Bob Carey Bridge is a really major, probably one of the largest pedestrian bridges in the world over the Missouri River, and it's S-curved, and hopefully this will play. It's a little video. It gives you a sense of what the bridge, it's a little better than still images. So the bridge is curved in an S configuration, yeah, that's maybe the best view of it, and it spans most of the river, not all of the river, and it's been a tremendous, you wouldn't think that people would, the bridge is almost a quarter of a mile long, or half a mile long, I should say. You wouldn't think that people would walk a half a mile in the Midwest, but they do. It's been fabulously successful. It's so curved, yet there's not one curved member in the bridge at all, okay? Every member is piecewise straight, and it's also made out of the same rolled sections. We typically weld beams together for bridges. I don't know why. We never used rolled sections like we do in buildings. So this was adapting this idea of, why shouldn't I be using rolled sections? They're already fabricated, and so there's no welding in this, yeah? So there's no welding and no fabrication. So anybody really, in terms of fabrication, could build the bridge. The other little trick is that each section is exactly the same. So this fabricator is building the same section over and over and over again to get you a complicated curve, what seems like a complicated curve. Well, this saves obviously a tremendous amount of money. A similar project, this was a bridge that was twice its budget, and one that we had been involved in the concept design of the over-budget bridge. So this was one where you really wanted to get things right the second time. But we had come up with a way, and this is a bridge over an interstate in California, in a very high seismic area. And the trick here was, how do you build an interstate bridge? And for us, the trick was, you had to close traffic, interstate traffic, every time you erected a piece of the bridge. So you had to erect as few pieces as possible. So the tower is built in halves. And the 2 towers come out on one truck, and they're picked from one crane, and this tower was set. I was in Asia at the time when they were setting this. I was watching this. There's a beautiful webcam. I was watching them erect this. The erection took 2 hours. Yeah? So one night, one tower. And the superstructure was the same way. We had temporary supports between the traffic lanes, and so each section was set in one night. Yeah? So the entire bridge came together in only 20 nighttime closures. And you know a project's going well. This is the head of the Department of Public Works is this guy right here. When he's installing the last cable, that's a sign that the project is going well. Yeah? Usually he's yelling at you. Yeah, the fact that he's out there putting the cable in is a good sign. So this project was fabulously successful, but it incorporates a little bit of my past. And I grew up near sand and stone plants, and I lost the ends of my fingers on my right hand from a sand and stone plant. That's not the plant, but it's similar to that. And what we use to sort sand and stone, really to sort stone, is these triple deck screens. And I don't know if my father knows this, but the triple deck screens use these clamps, and the screens are relatively cost effective. So I use that for railings, yeah? And the railings on the Champlain Bridge will have screen deck on them. You won't know that it's screen deck. They're actually very nice looking elements, but they're also wonderfully robust, and they're actually tensioned so that you don't have to support them very much. So this railing on Mary Avenue was much more cost effective than the railing they designed. In fact, it was about 1/3 of the cost of the other railing for the old bridge. And so the last thing I'll say in terms of cost reduction is the Happy Hollow Bridge, which has got some DNA for the Crown Point Bridge. And that's that here this is a bridge made out of 2 rolled beams, 2 rolled sections bent. So in the case of the Bob Carey Bridge in Omaha, nothing was bent. In this case, everything was bent, okay? But it was bent steel in that we used the same rolled beam. So this is essentially one rolled beam, and the lateral bracing is an I section cut in half and bent, yeah? And the idea here is that you can be, this is the CAD details, but the idea is the entire bridge, an entire span came on one truck. Here's all of the pieces, again, fabricated with very little welding, and the final product is really an unusual bridge for California, where they do mostly in concrete. This is weathering steel, so it creates its own protective layer. But here again you see, this is also a study on how many cables we can use. Now, how did construction get influence the design of the Crown Point Bridge? And this is the idea of floating in the arch and using the existing approaches, or the new approaches, as the crane, okay? So there is no crane for lifting the arch, and this is supposed to happen. I know people will ask me this, so I'll say it now. This is supposed to happen sometime this week, probably late this week, Wednesday or Thursday is where they're hoping, yeah? Now, I'll play the video because it describes exactly how the arch is being used to lift itself, okay? So this is exactly the way the contractor chose to lift the bridge. This is the last piece of the arch, yeah? It's actually used to support the bridge. We simply make a connection here, fly in a beam, and put a bearing underneath it, and we're done, yeah? So this is quite an unusual scheme, but it's a scheme that we integrated in the design. Now, the design was very fast-tracked. This was a 10-week design period, the fastest we've ever designed a major bridge. But that doesn't mean you can forget about construction. If you get the construction right, you'll get the costs right. And so the other big advantage from a construction perspective is you can be building the arches, I should say building the arch and building the approaches simultaneously. They're 2 separate efforts, and you can see the contractor adopted to do exactly that, building the arch in Port Henry and obviously building the approaches on site. 2 simultaneous activities. When we're trying to save time, this is the best way to do it, yeah? And then just some of the details. Part of what we want is a durable bridge, right? The existing bridge lasted 80 years. We want at least 80 years out of the new bridge. And part of it is making the elements of the new bridge that can wear out replaceable. So this is putting granite facing around the piers. The granite actually matches the concrete better than I could have imagined, so it's hard to tell that it's granite. but each granite piece is designed to be replaceable. Yeah? So this could be damaged. It's a protective element. It's designed to be replaceable. The steel is coated with a thermal spray coating. We're actually not painting it. We're spraying metal on it. And the metal we're spraying is actually 85% zinc, like galvanizing, and 15% aluminum. That's better than galvanizing. Yeah? So here again, we're trying to get a longer life from these critical elements, and every bit of the bridge is metallized. In just some construction slides to give you a sense of things, you have 100-foot deep shafts, so these actually have to be spliced. You have water-based cranes, so you have pick size limitations. We were coring about 12 feet to 15 feet into the rock. The rock is wonderful quality here. I just wish it were closer to the water line. Yeah, so we had very deep foundations. We hit 2 obstructions from the existing bridge, and it probably cost us a month in schedule clearing one of the obstructions. But other than that, we really didn't have any major challenges with the foundation. This technology of drilled shaft construction is probably the most used technology nowadays. Pier construction, that sloping face is a little bit of a challenge from tying reinforcement, yet you can tell very clearly these are not unreinforced piers. There's boatloads of reinforcement in the piers, and this is part of efficient design. The pier shape, I should say just a few words about. The pier shape itself is the same. Yeah, if you imagine a rubber band here, as the piers get shallower, you're just cutting off so that the same formwork can be used for every pier. Yeah, in my view, that's also being respectful of the contractor and what work the contractor has to do. A lot of the work was done in the winter, and we were planning on that work being done in the winter. Pier construction is probably the best thing in winter concreting. The flooding caused us some challenges, as you can imagine, with foundation construction. So the cofferdam here is flooded, waiting for the lake level to go down. Probably cost us a month or so as well. This pier construction, because the pier does not change width, you could use the same formwork everywhere. Yeah? So not only can you use the same formwork, but it's also simple gang forming. This is the simplest formwork we have. Yeah, so even though the pier has quite a shape to it, in the other direction, it's dead straight. Yeah, so it's quite easy to construct. Superstructure erection has gone without a hitch, and the contractor Flatiron is really expert at steel erection, and they did a beautiful job. And this is pretty well where we're at now with the superstructures ready for the arch. Decks have been poured on most of the superstructure now. Yeah, so the decks are ready on the approaches, and the arch span itself will take precast panels, so we're not pouring so much concrete on the arch span. The arch span is almost done in terms of erection. If you're out there, you'll see the cables look a little saggy. That's because they're tensioning them as we speak. Before it's floated out, the cables will be more taut than they are now, although not completely taut until we put the deck panels down. So it's sometime this week. I'm betting Thursday as opposed to Wednesday, but it could be anywhere in that time frame. And if the weather's good, if the weather's bad, it may be delayed further. So with that, I'd sure like to answer questions. And if there are people who are interested in other things I'm doing, I have a few more slides if you're interested, but I certainly don't want to take up any more time than I have. Thank you. Are there any questions? And I'll try to repeat the question. None from my father. Yes. This is about the screen deck, I imagine.